Today we're going to talk about electron configuration, which is what you started learning about yesterday when you were working on the POGO. Electron configuration tells you where the electrons are located around the nucleus. And so we arrange these in this order: energy level, sublevel, orbital. And this is just getting a closer location of where the electron is. So if an electron configuration tells you where the electrons are, an energy level would be like the state, the sublevel might be like the city within the state, then an orbital would be like your actual street address. So we're getting closer to the location of the electrons and where we can find them. Energy level is going to be like the floor of the hotel. So from the POGO yesterday, as you were trying to put borders into the different rooms, the energy level would be similar to the floor. So electrons exist in areas called energy levels. As you move further away from the nucleus, we get more energy levels. As you can see over here on our Bohr model, each individual circle is an energy level. So the further we go away, the more energy levels we have. Energy levels are made up of these things called sublevels. When you were working with the POGO yesterday, the sunny room and the pink room represent two types of sublevels, the S and the P. There's actually 4 different types: S, P, D, and F, and all they really refer to are the shapes of the places where we find the electrons. Now these sublevels do have mathematical relationships to determine their shape. Each sublevel is made up of an orbital. Yesterday the orbitals were represented by the bunk bed. If you remember, each bunk bed can hold 2 people. Same thing goes for an orbital. Each orbital can hold up to 2 electrons. In the s orbital, there's one type of orbital. You can see over here in the picture. We can hold 2 electrons total in the s. The p orbitals, there's 3 of them. They can hold a total of 6. D can hold up to 10 since there's 5, and F has 7. We can hold up to 14. Now each orbital does have a different type of shape. The s orbitals are spherical in shape. The p orbitals, we like to call them dumbbells. The d's, most of them are clover shaped. I know if we look over here, this one starts to get tricky and complex. And if we look at the f shapes down here too, those really start to get out of control. You don't have to memorize these shapes, but you do need to know that they are different. So each letter, S, P, D, and F, are going to give you different shapes of orbitals. Now this is going to be the part where we show you how to write an electron configuration, or how to read it also. You've got the different numbers and letters within this. Each thing is represented by a specific part that we just talked about: the energy level, the sublevel, and then the number of electrons within that orbital, or that sublevel. So energy level is equal to the period number. So since this is energy level 1, it's going to be in period 1 on the periodic table. This tells us that there's 1 electron within that sublevel. And so then we've got the S that we're working with on here. What element has an electron configuration of 1s1? Well, the way we figure this out is we go to our periodic table here, and we look for period 1, and we look for the s orbitals, which are this area over here, and then we're in the first position. So this element right here is hydrogen. Hydrogen's going to have 1s1. Now if hydrogen is 1s1, helium's going to be over here at 1s2, lithium will be 2s1, and we just continue on down the road. Now over here we've got our s block. Over here we've got the p block. And notice that even though helium is over on the p side, it really does belong right here. We've learned before that since helium has a full outer shell, we consider it a noble gas, and so it's going to be on that side. D block is in the middle, and then F block is down at the bottom. Something we want to point out here, if you notice the D block here, we go from 4s, and then it drops back down to 3d. We were at 1, 2, 3, 4, but then we make that transition to 3 at this part. And there's a reason for that, and we'll talk about it in a minute. But you do need to know that when we, after 4s right here, it drops down to 3d. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then right back here, it picks back up at 4p again. And then it does the same thing after 5s, then it goes 4d, and then back to 5p, 6s. But then at this point, we get 4f first. So it goes 6s, then 4f, and then 5d. And then it goes back to 6p. Now the next things we're going to look at are the rules for when you're writing electron configurations or orbital notations. And don't get confused by the names. You just need to really know the rule. I don't care about the names or memorizing those. The Pauli exclusion principle says that electrons or orbitals can only hold 2 electrons. And the way you did this yesterday was the bunk bed. The bunk bed can only hold 2 people. If you can just remember that each orbital can only hold 2 electrons, then you've learned the rule. The next rule is what we call Hund's rule. We use these arrows to represent electrons whenever we're drawing what's called orbital notation, or we use lines or boxes for that. And each orbital must have an electron in it before we start to pair them up. This is the same thing with the bunk beds. You had to fill up the bottom bunks first before you could put people into the top bunks. The last rule is the Aufbau principle, and this is what we call the lazy electron rule. Electrons enter the lowest energy levels first. When you were doing the hotel, the bottom floor had to be full before the top floors. And earlier I told you why 4s, then it drops to 3d. I told you why I'd tell you that. If you look on here, we can see 4s is slightly lower than 3d. What we see on there. So because 4s is lower, it goes 3s, 3p, 4s, and then 3d, back to 4p. So even though it looks like 3d is first, because 4s is lower in energy, we're going to fill 4s first. And it's the same thing on the periodic table right here. We go 3s, 3p, 4s, and then drop back down to 3d, and then 4p. And it's all because 4s is a lower energy state than 3d. And there are 2 ways to memorize the order of the electrons that we fill in. First way is you can write it like this, where you go 1s, 2s, 3s, 4s, 5s, 6s, and you can repeat it for 2p, 3p, 4p, 5p, 6p. And then if you draw lines like we show here with the arrows, diagonal down, if you follow this, we go 1s, and then we reach the end, so we'll go to the next one, 2s, then 2p, follow the arrow down, 3s, 3p, follow the arrow down, 4s, and then 3d, 4p, 5s, 4d, 5p, 6s. So every time you reach the end of the arrow, you just go back and start up. That's one way to memorize it. The other way to memorize it is the way I prefer. I like to write my S, P, D, and then F down here. And then if you follow it from left to right, it'll tell you the order. So we go 1S, and then we reach the end. And then we start right here. It goes 2S, and then next is 2P6. We reach the end. And then 3S, and then 3P. We reach the end. 4S. We reach 3D, then 4P, and we just continue it like that. If you can remember that this area is S, this is P, this is D, and this is F down here. To me, this is a much easier way to remember the order. Now we want to show you how to draw the orbital notations and write the electron configurations. We're going to start with hydrogen. Hydrogen's the first element. It has 1 electron. So we'll draw an arrow in 1s. And then the way we write that is 1s1. 1 for the first energy level, S because it's in the S block, and then the 1 at the top because it has 1 electron. Helium has 2 electrons, we go 1s1, 1s2. We draw our up and down arrow. Remember, the rule says you can have 2 electrons in an orbital, and they have to be opposite direction because electrons spin differently. And we write 1s2. Lithium's Li, and it's 3 electrons. We go 1, 2, and since we're full here, we've got to go up to the next row, and that's where we go to 2s. So 1s2, 2s1. Carbon's going to have 6. We go 1, 2, 3, 4, 5. Now remember, each orbital gets its own electron before we start pairing up. That's why that last electron here goes into this box. 1s2, 2s2, 2p2. Nitrogen's going to have 7. We go 1, 2, 3, 4. Those are full, so we go up to the next one. 5, 6, 7. And we write that as 1s2, 2s2, 2p3. Oxygen's going to have 8. We go 1, 2, 3, 4. Those are full. 1, 2, 3. We have to fill those up first, and then we go and fill our last one. And we write that as 1s2, 2s2, 2p4. Fluorine's got 9. We go 1, 2, 3, 4, 5, 6, 7. Then we go back and pair 8, 9. It's going to be 1s2, 2s2, 2p5. And then finally, neon has 10 electrons. 1, 2, 3, 4, 5, 6. If you notice one thing over here, these exponents add up to give you the total number of electrons. It's a way we can check our work. 2 plus 1 is 3. Lithium has 3 electrons. 2 plus 2 plus 2 is 6. Carbon has 6 electrons. We can check our work like that. 2 plus 2 plus 3 is going to be 7, just like nitrogen. 2, 2, and 4 is 8, 9, and 10. We're going to practice on sodium now. Write the configuration for sodium. The first thing we're going to do is locate sodium, and it is right here. And then on its periodic table, it's right here. We're going to start at the very top, and we're going to write it in the order from left to right. So we're going to write row, which is 1. We're at the S block, and then we count them up. There's 1, 2. So it's 1s2. We've reached the end of the row, so now we drop down to the next one here, and we're at 2, and then this is still S, and there's 1, 2. We reached the end, but we got to keep going here. What row are we in? We're in row 2. This is letter P, and then we count up all the ones we see. 1, 2, 3, 4, 5, 6, and then we drop down to the next row. And this is row 3, still letter S. And instead of 2, since this one's in the first position, we're going to call that 1. So it's going to end on 3s1. If we wanted to draw the arrows for this, it would look something like this. So this is 1s, and it has an up and a down. This is 2s, it has an up and a down. This is 2p, remember we go up, 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 and then we go down, 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 and then we end on our 11th right here at 3s. That's the electron configuration right here. And then the arrows is the orbital notation. We're going to work 2 more here. We're going to write the configuration for iron, and then we want to draw the orbital notation also. First thing we want to do is find iron. It's right there. If we count that over, it's 1, 2, 3, 4, 5, 6 into the D block. So 1, 2, 3, 4, 5, 6. It's right here on this map. We're always going to start up at the top with hydrogen. 1s. We count them 1, 2. We've reached the end. We drop to the next row. This is row 2, letter S, and it's 2 wide. Then we continue on. We're still in row 2, letter P, and we count them up 1, 2, 3, 4, 5, 6. We reach the end, we drop to the next one. Row 3, letter S. There's 2 of them. We continue on. We're at row 3, letter P. And then there's 1, 2, 3, 4, 5, 6. We drop down to the next one. It's 4, S. And it's still only 2. 1, 2. If you didn't notice, it'll never be more than 2 because S is only 2 blocks wide. And then remember, after we reach 4S, it drops down to 3D at this point here. So there's 4S, 3D, and then we'll write 3, letter D, and it was 6 over 1, 2, 3, 4, 5, 6. If we draw the arrows, it's going to go up, down, up, down. Remember, P has 3, so it's 1, 2, 3. Go up, 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 down, down, down. S is 1 wide, up, down. P is 3, 1, 2, 3. Up, 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 down, down, down. S is up, down. And D was 5 orbitals. 1, 2, 3, 4, 5. So it goes up, 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 and then on our 6th one, we'll go right back to the first one. This will be the last one we work. Write the configuration, draw the orbital notation for bromine. Bromine's right here. It's in the 4p5, right there. And then we're going to start our same order. 1s2. We reach the end. We're at row 2, letter S. It's 2 wide. And then row 2, letter P, there's 6 of them. We're up to 3S, 2, 3P, 6, 4S, 2, and then we said it drops down to 3D, and if we count them, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it goes back right here to 4P. 4P, and it's 1, 2, 3, 4, 5 over. If we draw the orbitals, S is 1, P's are 3, S is 1, P's are 3, S is 1, D is 5, 2, 3, 4, 5, and then P is 3. It'll be up, down, each one gets one, and then we go back and fill the doubles, and up, down. We can go to the next, up, 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 down, 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 up, down, and then we get to D. Remember, 1, 2, 3, 4, 5. Then we can go back and fill those in. And then our last one here, 1, 2, 3, 4, 5. The last thing I want to touch on is students always ask, well, why can't we just write 4p5 instead of writing all this extra stuff? Electron configuration is not about just one electron. It's the location of all the electrons. The configuration tells you the sublevels, the energy levels, the orbitals of every single electron. So it's not just about identifying an element or drawing it out, but it's more about telling you the location of every single electron. So even though it's tedious and a lot of work, we do have to write out the entire notation for that.